Hello, welcome to another video. Here I will introduce an article about a practical about how to visualize support vector machine and how to interpret it. So, as is mentioned in the article, support vector machines are often considered black boxes, and if you especially use Python to get results, you may not be familiar what is going on and what are the steps and what is the science behind this model. And this picture has nothing to do with this article, but it looks like somehow those graphics, like in here, I guess. Um, and thanks for the author for providing such good article. And this article contains the following sections, like introduction to models and how to interpret engineered feature space, which are utilizing kernels, support vector machine kernels, and these are used in Python application of it too. Techniques for evaluating the performance of high-dimensional classification boundaries, practical options for working with large class imbalances, and how much data you need to train and support vector machine. I think you will find a lot of answers for a lot of questions by reading this article. So in machine learning, linear classifiers are any model in which there is a single hypothesis function which maps between model inputs and predicted outputs. So these are features of example, and this is the output decision function. The primary advantage of linear models over neural networks is that the feature weights directly correspond to the importance of the feature within model. Thus, it is easy to understand what the model has learned. So training L1 regularized regression model, it is immediately obvious that most of our features in our dataset are totally irrelevant to predicting our output. It's clear that features 0, 1 make positive contributions to the model. And while the presence of features 2, 3, 4 is not clear, in given example result in negative contributions to the output. So we can see this regularized LCR feature importance. So at the core of any linear model is a dot product between the input example and the parameter weight factor. In the case of linear regression, this is the entire hypothesis function, whereas logistic regression feeds the dot product through a sigmoid function such that the output is between 0 and 1, and hence is suitable for binary classification problems. So that when considering classification problems, the downfall of linear models is that ultimately the decision boundary is a straight line, plane or hyperplane with coefficients equal to the model's weights and parameters, and thus can only classify that data which is linearly separable, which could be a big limitation when working on more complex analytic problems. So here linear model, and here is not that linear looking model. So, and in this feature x is the only independent variable, and we have to predict the other variable which has an inherently nonlinear relationship with x. We can engineer the other features to improve our fit to y. So that, and here, and the article explains further how to do it and what is the necessary calculations to reach the conclusion. And so it says examining effects of various factors on concussions. So these are increasing concussion probability by role. So these some of them do not really affect the result output. I took all the negative examples and averaged the probabilities across them. I have highlighted the areas in red for each feature where players were most likely to receive a concussion. A trick if you have a bunch of hot encoded variables like player roles is to aggregate them into a bar chart and just look at the net change in probability between when the feature is present and not present. So some of them are, as you see, negative, some of them are positive, and by changing it, I think it's possible to change the prediction results and we can create better models. And thanks for watching this video. I hope you enjoyed this video, and I will put this link in the description so you can read all article and understand it. Have a beautiful day. Bye bye.